All right, so we were designing a beam and we had chosen a beam section of ISLB 550. Okay, so the overall depth of the beam was 550 mm, thickness of flange was 15 mm, the width of the flange was 190 mm, and the thickness of the web is 9.9 mm. We had checked whether this beam is under high shear or low shear, and based on whether it is in high or in low shear, we had also calculated the design bending strength of the section. We had checked for deflection, and in the previous video we had also checked whether the beam was safe against web buckling or not, right? In this video, what we are going to do is that we are going to check whether the beam is safe against web crippling. So before going into the calculations of web crippling stress, let us first see what is web crippling. Now, see in the first diagram, this is an I-beam on which vertical loads are being applied. These vertical loads are compressive in nature. Now what happens due to the action of this vertically compressive loads, some localized stresses might get concentrated in the portions of the web which is nearer or closer to the top or the bottom flange. Okay. Due to this localized stresses, what happens? Some localized deformations occurs at the web which is near the root junction, okay, which is near the bottom flange or the top flange. So these occurrences of localized deformation in the web of the beam is known as web crippling, right? And how do we calculate the critical stress for web crippling? It is given in clause number 8.7.4 of page 67 of IS 800/2007. So it says that Fw is equal to, this is the critical stress against crippling, this is equal to B1 plus N2 into Tw Fyw divided by gamma m0, right? So let's go to this page number. Okay, so so this is 8.7.4 and it says bearing stiffeners. So what happens in order to resist or in order to provide resistance to the web against web crippling, we provide bearing stiffeners, and initially we always provide a support on which the beam rests. Now this support also acts as a bearing stiffener, right? So let's read it. Bearing stiffeners should be provided for webs where forces applied through a flange by loads or reactions exceeding the local capacity of the web at its connection to the flange, Fw given by this formula, B1 plus N2 into Tw Fyw by gamma m0. What is B1? It is the stiff bearing length. It is given in 8.7.1.3. I would ask you to look it up. Okay. Then we have N2. Value of N2 is how much? Length obtained by dispersion through the flange to the web junction at a slope of 1:2.5 to the plane of the flange. Tw is web thickness, Fyw is the yield stress of the web. Okay, these two values you know, but B1 and N2 you have to calculate. Let's go into the problem now. So we have the web crippling, critical stress for web crippling as this, B1 plus N2 Tw Fyw by gamma m0. Now what is B1? B1 is the width of the stiffener or the support that we are providing. You can assume the value of the width of the stiffener as 100 mm or 150 mm. Okay, we are assuming it to be 100 mm. B1 we are assuming it to be 100 mm, right? And what is N2? See, due to this stiffener or due to this support, certain load dispersion or strength dispersion takes place, and this dispersion occurs at what occur it the strength dispersion should take place at a slope of 1:2.5. The slope is already mentioned in the code. Okay, so the load dispersion due to the stiffener takes place at a slope of 1:2.5 up to which length? From the bottom of the flange to the root, to the top of the root. Okay, this is my flange and this is my root, right? So this load dispersion should take place at a slope of 1:5 from the bottom of the flange to the root of this beam, the bottom root of the beam. Okay, now what is this root? The root I will show you from a diagram. Okay, let's find an I-beam. Okay, so see, this is an I-beam. Here the root is not mentioned, but the root, this is the flange. Okay, this is the flange. The thickness of the flange is taken at the mid section of the flange, right? This is my TF. Okay, this is TF. And what is the root? The root portion is this curved portion. Okay, the curved portion which is at the junction of the flange and the web. So this portion is known as my root, and the value of this radius of root, okay, I'm not able to draw it properly. Anyway, the curved portion which is at the junction of the flange and the web is known as the root, and the value of the root radius is given in your IS code. It is also given in the handbook for different sections. So for IS LB 550, our root radius, for ISLB 550, the root radius is given as 18 mm. Okay, so how much is N2 going to be? See, first you have to calculate this distance. You have to calculate this height. How much is this? This is my flange. This is the thickness of my flange, which is TF. And this is my root radius, which is given as R. I will again show you. This is R. This much is R, right? And this much it is TF. This is the thickness of the flange, and R is the root radius. Okay, so the total height is how much? The total height is going to be, the total height up to which the dispersion takes place is going to be, I'm denoting it as H2, which will be equal to TF plus R. How much is TF? What is the thickness of the flange? It is 15 mm. Okay, this is equal to 15 mm plus, and the root radius is also given, it is 18 mm. You can find the value of root radius from the code for with respect to this section. Okay, so this is my total height up to which the dispersion is taking place. So how much is it going to be? It is coming out to be 33. This is equal to 33 mm. Clear? Now what you need to calculate this N2. Okay, in order to calculate this N2, what you have to do, you have to just multiply 2.5, because the slope at which the dispersion is taking place is 1:2.5. So if you multiply the value of this H2, the value of this H2 with 2.5, you will get this horizontal length, right? So N2 is equal to 2.5 into H2, and if you calculate this 2.5 into 33, this value is coming out. So the value of N2 is coming out as 82.5. Okay, this value is coming out as 82.5 mm, and this B1 we are assuming, you can assume it to be 100 mm or 150 mm. We are assuming it to be 100 mm. So now we have the value of B1 and N2. You know what is TW? TW is the thickness of the web, which is given as 9.9 mm. FYW is 250 mm, and the partial safety factor for the steel of the web is 1.1. So if you calculate it, it is coming out to be 410.6 kilonewton. So this is the critical stress beyond which web crippling will take place. Now you have to compare the value of this critical stress with the applied shear, applied factored shear, I should rather say. So this applied factored shear value is far less than the critical stress of this beam for crippling. So hence the section which we have chosen is safe against crippling as well as against buckling also.